And I think one of my first interactions with complex dynamics was watching Buddy Krieger on number 5. So thank you. All right. So without further ado, let's consider a holomorphic term which has a fixed constant 0 of rotation under e to the 2 pi I alpha plus some terms for alpha irrationally. And this is basically the example that I'm interested in. And so in this situation, f has a 2 pi alpha rotation in the tangential direction. So I mean, it really does rotate things around fixed points of 0. But on the other hand, it's if we assume it's not linear, if f is not linear, then there will be non-trivial radial movements. So as we move, as we rotate around, it can go further or closer away from 0. Non-trivial radial movements. And so to give a kind of picture of what this means is just you can imagine if you have points, you have to solve 0, and you have the map iterating on points. What it often does is it will rotate, it will look like it's rotating around, but then there'll be some iterating points which gets rather close to 0. So that modulus is not exactly the same, like whether as a normal rotation on the circle that they expect.
And so then the big question that we kind of want to think about here, that you always want to understand when you're trying to understand dynamics near a fixed point, is what is the local dynamics? So the big question is, what is the local dynamics near 0? And this is kind of like a vague question because what does it mean? What is the local dynamics? And I've kind of intentionally left it that way. But what I mean is, if we look at the points for which their orbits remain close to 0, how can we understand those? What's a reasonable way to understand it? And so one of the key approaches is to ask, is f linearizable? So in particular, we say that this function is linearizable if there exists a analytic map going from some open set, which we call delta f, which will contain the fixed points at 0. And this will be an analytic homeomorphism that will go to C such that phi of 0 equals 0. And in particular, sorry, I'm going to write it around here a bit awkwardly. In particular, phi will conjugate to f to a rotation by e to the 2 pi alpha. So z is going to be equal to e to the 2 pi I alpha phi of z. And so this is... But phi is like a change of coordinate. It's like a change of coordinates. Yeah.
I don't know. I heard only.
But it's a biholomorphic. Biholomorphic. But it's also homeomorphism, right? So, yes. Yes. No, it's also a biholomorphism. But as I'm sort of going to get into, if we relax the assumption of needing holomorphic change of coordinates, then you end up with answering other questions, right? And so then many people have studied this. How am I going to do this? So I bring this up. Sorry. Wait. I'll write below. Sorry, it's just getting used to giving a board talk. And so then, and we denote sigma f to be the maximal domain upon which this is possible. So this is called the Siegel disk in general, right? And it is a result by Siegel is that case and also Kramer that there are very classical results that examples exist. Let me write through this. Examples exist for which this maximal domain delta f is equal to 0 and also not equal to 0. So this is like a kind of this means that you really get a full range of possibilities. But when it is linear, obviously, then you can understand the dynamics of points that are within this set very well. But then maybe there are other points outside of this set which also stay close to 0. So how can you understand the dynamics of those? And in particular, it is a theorem by Fatou and Monet. Well, not collaboration, but a combination of theorems by them, that for all such examples, there exists a special critical point, which I'm going to denote by C for the rest of this talk. There exists a special critical point such that the omega limit set, so does everyone know what the omega limit set is for a point here? Yes, good, yeah. So this is the closure of the orbit, or the forward orbit of this critical point. There is a special critical point such that whether we're in the Kramer case, which is the example where this delta f is equal to 0, or the Siegel case, this, regardless of the instance, this will contain the boundary of our Siegel disk or not Siegel disk, and also it will be recurrent to itself. So this will also be exhibiting, the orbit of this critical point will also be exhibiting dynamics that will be staying local, semi-local to the fixed point at 0. So we want to try and understand this. Yes. You should be maximal, yeah. And it's also a separate theorem by Lubitsch that, in fact, almost every, for the rational case, so I'll just put that in, for f rational, almost every point in the Julia set, so I assume someone earlier on this week defined what Julia set is, almost every point in the Julia set will converge in spherical will converge, I should say, converge to the post-critical set. And in particular, what this means is that if we study these this set omega of C, we really do understand the dynamics of the points that stay near 0. So understanding this set omega of C is incredibly important. Converge to the post-critical set. Okay, so this is the setting, and now I can give the definition of what an irrationally different attractor is. So definition. Yeah, it's orbit. Yes, sorry. Almost every point of view will converge in orbit. Yeah, sorry guys. It's my first time giving a board talk, so I'm just I tried to prepare a lot, but it's new for me.
Possibly almost every.
I think it's in the Lebesgue sense. Yeah. It's like an old theorem from like the 80s, I believe. Yeah. It's like a very general.
A zero measure.
Oh yeah, good point. Yes, I suppose it means.
Yeah, it only makes sense when Julius has expression. Okay. Yeah, which exists.
Yeah. And you also need the geoset to not be equal to the whole Riemann sphere for this result to follow through. Yeah. Okay. So definition, this set, omega of t, is called the irrationally indifferent attractor for all of these reasons. And this is basically the fundamental object of study you want to understand if you want to understand these irrationally different fixed points. All right, brilliant. And sorry, my notes have gotten a bit mixed up. And so then the next question is how can we even begin to start studying this? So it turns out that, as you might expect, a lot of these objects have a very deep connection to the arithmetic of our irrational number alpha. So as kind of Alexander already touched on, each irrational number alpha has a continued fraction expansion, but actually there are many continued fraction expansions. They depend on the fundamental domain that you start with. But they're all generated by the action of the Gauss map, which is sending alpha to 1 over alpha. And then you have to choose whether you do mod z or whether you use some other construction. And in the construction that's most convenient for this, you include plus minus ones everywhere. So you get this alpha is going to be equal to some initial A0, which may, and we want to enforce every parameter to be positive. So all AI are positive integers. And then there's a way to write this as plus minus A0 plus minus A1 plus minus 1 over A2 ... And this essentially will give you a sequence of positive integers. And the plus minuses will be determined by the nature of alpha. And so this is kind of a modified continued fraction expansion. And then it's basically a theorem by Bruno. This is also classical. That if this Bruno sum, which is defined by log 1 over alpha 0 plus alpha 0 times log 1 over alpha 1 plus alpha 0 times alpha 1 times log 1 over alpha 2, etc. If this is less than 30, and we call this a Bruno sum, then f is linearizable. And conversely, Yoko's proved that for quadratics this is optimal. However, this still does not fully settle the question of what the local dynamics around such points is, because in particular this critical point may not lie on the boundary of the Ziegler disk. If it does, then you're in a perfect good situation. You have rotation, you have, and it really does just behave like you're rotating around a unit circle. But this critical point may be outside it. So how do we understand those orbits? So this is optimal. And so for this reason, this is where I want to try and introduce the idea of a model. So this is basically work by, where's the eraser? Ah, right, so thank you. And so maybe I'll keep the statement of what f is up. Just erase this stuff. So it's a result by Chiragi that there exists a model, we call it, a model for this omega limit sets together with the Ziegler disk, if it does have a Ziegler disk, defined as T alpha acting on M alpha to M alpha. And so these are not, I'm going to explain briefly what these are. So these are basically model maps. So they are not holomorphic. They're actually, so T alpha is a homeo. And M alpha is a star-like shape around 0. So it still includes 0 as a fixed point, this map, but it is no longer a holomorphic map in any sense. It's just a homeomorphism acting as 2 pi rotation, acting as 2 pi alpha rotation. And it satisfies some special geometry. So I'm going to explain what that means in a second. But essentially, this results. So you might ask, like, why I can claim that anything is a model for anything, and I don't have to. If I don't justify it, then I can say that anything is a model, and it doesn't matter. But the point for this model is that in the unicritical example, for which we only have one critical point satisfying this Manet theorem, it is a conjecture and both a theorem in many cases that this model is actually conjugate to the dynamics of these irrationally different maps for all rotation numbers. And it's a theorem for many specific examples, which I'm not going to go into right now, but Alexandra briefly touched on the concept of high type. So if it's of high type, then it can be proven that this really does reflect the dynamics. And why would we do this? Why would we say this? Well, this only depends on one parameter now. So it doesn't matter what all the higher order terms do. It only depends on one parameter at this irrational number, and this determines all of the dynamics. So it's quite a remarkable result. And the reason I try to frame it in this kind of awkward way is I try to connect it to the idea of linearizability. Is that, like, this is almost an extension of that notion. If this is linearizable, the linearizable portion will be contained in this M alpha, but it will also describe the dynamics outside. And why would that dynamics be interesting? Well, I'll hopefully explain that in a second. Okay. But this raises the question, what about other examples? So this result only works and is only even conjectured to work in the unicritical case. So what if you have two critical points which are interacting with our fixed points, as I like to call it? So what if there exists two critical points, C1, C2, such that they're both recurrent to themselves. So Ci is in the magnetic of Ci for all I. They're both recurrent to each other. So C1 is in the omega limit set of C2. C2 is in the omega limit set of C1. And they also both satisfy that their omega limit sets are equal. So I guess a lot of this consequence of this, and contains the boundary of our zeta disk. So now, because this could actually happen in many examples that we call unicritical, if you have a critical point that comes in from very far away and then is maybe not recurrent, but it still interacts with the boundary of your zeta disk, or if you have a non-linearizable fixed point. But the recurrence property ensures that actually these two critical points somehow are equal. They're of equal importance. So you can't degenerate to the unicritical case because you really have to take into account the orbits of both. And so then, in these examples, it's possible to think about what I call an internal angle. So there exists an internal angle iota, which is just a real number, it doesn't have to be irrational, between C1 and C2. And so in the example where you have a Zeal disk, for which both critical points are on the boundary of the Zeal disk, so this is one example that will satisfy this case, this really is just the angle that you get from the linearizing map. You have an iota here, but the iota is exactly the iota you get from the linearizing map, which gives you an iota over here. And then the new results, which I'm just going to at the end of the talk, is that, in fact, you can write down a new model for this bicritical case that depends on now two parameters, this alpha and this iota parameter. So I drop this over here. So, theorem. There exists a bicritical model denoted by M alpha iota, that's the set, and you have a map T alpha iota, which acts on M alpha iota to itself, such that, once again, our T alpha iota is a homeomorphism acting as 2 pi alpha rotation, so this is the same. It now satisfies it has bicritical geometry, which I'll hopefully have time to explain in a second. And furthermore, now an extended action of the Gauss map comes into play, which acts on this iota parameter as well. So we now have alpha iota gets mapped to 1 over alpha iota over alpha. And in a very similar fashion to the continued fraction expansion, this gives you a sequence of numbers, alpha 0, iota 0, alpha 1, iota 1. And essentially everything in the model comes from this sequence of arithmetic. And the model really does now depend on 2 parameters. So how does this work? So, and what consequences does it have? So in some senses, many things are the same as the unicritical case. So for instance, it was proven by Chiragi that in the unicritical case, there is a trichotomy of topologies, which only depend on alpha. And in fact, it turns out that this iota parameter does not affect this trichotomy. So the trichotomy is that if alpha is a Hermann number, which I'm not going to go into the definitions, but it's a condition which basically ensures that the critical points are on the boundary of your Siegel disk, and it's contained in the Bruno case, which is if the sum, which I wrote down earlier, is less than 30, then the topology is of M alpha is just a Jordan domain. It's a domain with a boundary which is equal to a Jordan curve. And then on the other hand, if alpha is a Bruno but not Hermann number, we get something similar to what Alexandra was just talking about, which is a hairy counter set. So there's a Siegel disk on the center, but then there are many, many hairs that are kind of going off from it. And on the other hand, if alpha is not Bruno, we get what's called a counter bouquet. And so this is an example where there are many hairs just coming out of 0. And this is kind of like a model for M alpha. And what turns out to be the case is that this condition, this trichotomy, does not depend on iota. So the iota parameter does not come into play in this sense. However, even though topologically speaking, we have these 3 sets, this trichotomy of objects, the iota parameter does change other properties of the model. So I have very little time, but I'm just going to try and briefly explain a couple of differences. So the 2 key differences I want to highlight are that of dynamical differences and also geometric. So there is a modified Bruno function, which we call B of alpha iota, which is going to be equal to, now using the sequence that we had earlier, the sequence of alpha 0, iota 0, it's now equal to a modified Bruno sum, which includes both parameters. So you now have this 1/2 log 1 over alpha plus 1/2 log 1 over alpha 0 plus iota 0. Then you add plus alpha 0 times log 1 over alpha 1. 1/2 times log 1 over alpha 1 plus 1/2 log 1 over alpha 1 plus iota 1, and so on and so forth. And as you may notice, this is actually bounded above and below by multiples of the original Bruno function. So whether this goes to infinity or not does not change. depending on your choice of iota. However, its geometric value does change. And the geometric value of this Bruno function determines the closest possible approach of your orbit of your critical point. So in all these examples, I tried to mention how these radial movements can sometimes accumulate so that the orbit can get closer and closer to the fixed point at 0. Maybe I said critical point just now. And this Bruno function, it basically, if you take e to the minus b of alpha iota, this will tell you how close you get to, you can possibly get to 0. So if you have a critical orbit, the closest approach will be roughly of that value. And then the other key difference, which I will say very, very quickly, is that, well, for all of these models, they have a marked critical point. So T alpha, M alpha as a model, so the unicritical model, and also the bicritical model have marked critical points. Marked, so I put in quotation marks because they're not actually critical points for these model maps, but they are marked points nonetheless at +1. So they both have a marked critical point at +1. And the map, if you try and conjugate these two situations, so the conjugacy wait, maybe this is the wrong way to phrase it. A map that sends +1 in M alpha to +1 in M alpha iota is not necessarily a conjugacy. So this basically implies that, so to prove this statement, so in some examples, this map that sends a marked critical point to itself will in fact induce conjugacy. So for example, if you're in the case where it's Hermann type and everything is on the boundary of the Siegel disk and it's all linearizable and it's all like a rotation domain, then everything is conjugate, so it's all fine. But there will exist choices of iota when alpha is not of Hermann type, such that this map, this natural map that will send a critical point to itself, can no longer be a conjugacy. So this implies that there is some increase in dynamical richness, which happens for this iota parameter. And yeah, I was going to explain a bit about how to build the model, but I think I'm out of time.
So I'm trying to remember your T alphas, are they rigid rotations?
No, no, because they also have the tangential movements, right? So even if you have the linearizable case, they're never going to be a rigid rotation. They always have a, so I was going to say a little bit about the geometry, but they always have this extra geometry induced by the other repelling fixed points being close to 0. So that's basically how it works. Yeah.
So how much of the geometry, like these are homeomorphic models of post-critical set?
Yeah.
For like this Bruno condition we have here for the closeness of the critical orbit to the fixed point, the geometric condition.
Yes.
So are you able to transfer, or do you think it's possible to transfer geometric data from the model?
Yes, so this it's actually a big topic of conversation, even for the unicritical. So actually, David has a paper which is not published, where he basically proves that the conjugacy that takes that works with the unicritical model is C1 up until the critical point, and at that point you can perhaps get some crazy spiraling behavior, which make it, because the model is a straight line, it doesn't have any spiraling at the critical point. And so for this reason, we basically expect that these models should be nearly geometric. Maybe they fail at some points, but they should also reflect the geometry in a very kind of rigid sense. And so the kind of conjecture is not only is there a conjugacy, it's also that the kind of the distance away from zero of orbits over time should reflect that exactly that of the map.
Thanks.
So for value of alpha, how does your linear model variance iota variance? Like in particular, as iota goes to zero.
Yeah, so I could draw a picture. So I mean, obviously, one impact is this Bruno function which describes close approaches. As iota goes to zero, this looks like the original Bruno function because these 1/2 log 1 over alphas summed together to just get log 1 over alpha. So you have, and that's the summand for the original Bruno condition. But yeah, I mean, the picture that I was about to draw, which I didn't have time, is that in the iota equals 1/2 case, sorry, I'm in blue now for some reason, you have a picture of orbits which looks like a figure of 8 pattern. So the reason this emerges is because in the dynamical plane, you actually have 2 repelling fixed points close to 0. These are roughly of size square root of alpha. Sorry, it's just new pen. And this is when the 2 critical points are on either side of one another. And the orbits will follow basically this geometry under 1 over alpha iterations, and then you pass to what we call the renormalization that Alexandra was kind of talking about. And then you do this again, and you end up with a non-autonomous system of dynamical systems which extend. And then at iota equals 0, you get essentially the same unicritical geometry which gave us a Chiragi model, which has where 1 over alpha iterates will follow a circle offset from 0 by roughly alpha. So if alpha is very small, this close approach to 0 at iota equals 0 will be much, much closer because square root of alpha is going to be a much larger number. Does that answer your question a little bit?
Yeah, I guess maybe more specifically, I should ask about like, so, okay, not knowing what the model is the main question, but is there some regularity property for the models as iota varies?
Yeah, I think.
And are somehow all iota achievable? I guess that's what the question is.
Yeah, I mean, well, I mean, that's a whole other question of itself, actually, is like, to what extent these exist in the actual dynamical plane. Because the goal behind this project is basically, if there did exist a renormalization, which was the fundamental engine behind the unicritical example for the bicritical example, then this model, the goal is to see if this model works. But in the actual case, we only know for some examples. So for instance, all iota is achievable if you have a bounded type alpha. So this is a result of Zachary, but that's the very trivial example where everything is on the boundary of a Zieldis, so it all looks like a rotation anyway. But in general, this is kind of, this is kind of like a work in progress question, is whether all iota is achievable and exists. But if it does, and the renormalization structure follows it, then this model should basically follow through, is the idea.